In this problem, we have an infinite line charge that is perpendicular to the plane of the figure, having a charge density of lambda. A particle of charge q and mass m is projected in the field of the line charge from point P. The point P is at a distance r from the line charge, and the velocity given to the particle is perpendicular to the radial line at P. So we have to find the speed of the particle when its distance from the line charge grows to neta times r. So we need to find the speed of the particle when its distance from the line charge grows to neta times r. So result number 1 is that if we have a line charge whose charge density is lambda, the electric field due to this line charge at a radial distance of r will be along the radial direction only, and its magnitude will be lambda divided by 2 pi epsilon naught r. So clearly, as we can see, this particle will have some radial acceleration, and hence its radial component of speed will start to increase. So let's say when the particle's distance from the line charge becomes neta times r, its radial velocity component is vr, and its perpendicular component is, let's say, v theta, and its net speed is, let's say, v. So clearly there is only one force acting on the particle, and that is the force due to the electric field, and that is always in the radial direction, right? There is no force in the perpendicular direction. Using work energy theorem, we can say the work done by the electric force would be equal to the change in kinetic energy of the particle. Now the electric force is acting in this direction. So the work done by electric force would be QE dot dr. The electric field as a function of r is going to be lambda by 2 pi epsilon naught r, and the limits will be from r to neta times r. And after solving, we'll get the work done by electric field as this particular value, and the change in kinetic energy would be half m v squared minus half m v naught squared. And from here, we'll get the speed of the particle, which was asked in the first question, as this particular value. In the second question, they're asking the velocity component of the particle along the radial lines. So in this question, they're asking about VR. So as we discussed earlier, there is only one force, and that is always in the radial direction. So the net torque acting on this particle about the origin is 0, right? Because the line of action of the force passes through the origin, which means the angular momentum of this particle must remain constant. And as we know, angular momentum of a particle is simply m v naught times r perpendicular. So initially the angular momentum was m v naught times r, and finally it's going to be m v theta times neta r, and from here we'll get v theta as v naught divided by neta. Now clearly we can say v square equals v theta square plus vr square. So as we determine the value of v theta, once you solve it, you'll get the radial component of the velocity as this particular value, which is the answer to the second question. So if you enjoy the solution, please like and subscribe to my channel, guys, and thanks for watching.